Welcome to episode 10 of the Physiology 225 podcast. I'm your host, Dr. Jim Davis, and today we're diving into graded potentials. This is a foundational concept in understanding how neurons communicate. Graded potentials are the small, short-lived changes in membrane potential that occur in response to stimuli. While these changes might seem minor, they play a critical role in setting the stage for action potentials, which we'll cover in the next episode. So let's get started. To start off, we need to understand what graded potentials are. Well, simply put, graded potentials are changes in membrane potential that occur primarily in the dendrites and cell body of a neuron. Unlike action potentials, which are all or nothing events that we'll talk about on the next episode, graded potentials vary in magnitude depending on the strength of the stimulus. And here are three key features. They're localized, meaning they occur at the site of stimulus application and diminish in strength as they spread out. They have variable strength. So larger stimuli open more ion channels, creating bigger changes in membrane potential. However, graded potentials are short-lived, meaning they decay over time and distance. So this leads us to depolarization and hyperpolarization. Now, graded potentials can be one of these things. They can either depolarize or they can hyperpolarize the membrane, depending on the ions involved and their direction of movement. When the membrane potential becomes less negative, this means it's depolarizing. This occurs when positive ions like sodium enter the cell. This also occurs when negative ions, like for example chloride, if it were to leave the cell. Depolarization is also known as an excitatory postsynaptic potential, or EPSP, because it moves the membrane potential closer to the threshold needed for an action potential. Next, we have hyperpolarization. During hyperpolarization, the membrane potential becomes more negative. This happens when positive ions like potassium leave the cell or negative ions like chloride enter the cell. Hyperpolarization is also called an inhibitory postsynaptic potential, or IPSP, because it makes reaching the threshold for an action potential less likely. Now, to determine whether a graded potential is excitatory or inhibitory, you need to know both the charge of the ion involved as well as the direction of its movement. With graded potentials, we also come across the idea of summation, and there's temporal and spatial summation. Now, a single graded potential is not enough to trigger an action potential, or in other words, it's not going to be large enough for a threshold to be reached. Instead, neurons rely on the summation of multiple graded potentials to reach the threshold. And summation is exactly what it sounds like. We're just adding one graded potential on top of another. Now, we can classify these in two ways. So we've got temporal summation. Temporal summation occurs when a single neuron sends multiple signals in rapid succession. These signals can add together to produce a larger depolarizing or hyperpolarizing effect. Then we have spatial summation. Multiple neurons can send signals at the exact same time. These signals combine at the postsynaptic membrane, and they influence the overall membrane potential. It's important to know that summation can involve a combination of excitatory and inhibitory signals, and the net result determines whether the neuron reaches a threshold for firing an action potential. Along those lines, neurotransmitters and ion channels are really interesting. A single neurotransmitter can have different effects in different locations. It depends on the type of ion channel that opens at the location of the synapse or the junction. For example, acetylcholine is excitatory in skeletal muscle. It causes a skeletal muscle cell to have an action potential, ultimately causing muscle contraction. And this happens because it opens sodium channels and sodium goes inside of the cell. But acetylcholine is inhibitory when it comes to cardiac pacemaker cells because it opens potassium channels and potassium leaves the cell, ultimately reducing heart rate. Now, this versatility highlights the importance of understanding specific ions and channels involved at a synapse. So, as always, let's finish with our key takeaways. Graded potentials are small, localized changes in membrane potential that vary in strength based on stimulus size. Depolarization, or EPSPs, move the membrane potential closer to threshold, while hyperpolarization, or IPSPs, move it further away. The direction and magnitude of ion flow will ultimately determine whether a graded potential is excitatory or inhibitory. Temporal and spatial summation combine multiple graded potentials to determine whether or not a neuron reaches threshold. And so that's it. You've made it through 10 episodes. I hope this breakdown of graded potentials has helped you understand their critical role in neuronal communication. Join me next time for episode 11, where I will be discussing action potentials and how they transmit signals along a neuron. Until then, keep questioning, keep exploring, and stay curious.